Well, it's probability of independent events, basically. That's good enough. So, just as a reminder from yesterday, an event, independent events are such that the probability of an event does not change the probability of other events. Now, in the world of statistics, oftentimes the assumption of independence is made valid by randomization. So, for the most part, what we're going to do is we're going to do events randomly. So, you're like, oh, this was randomly selected. So, if they're randomly selected, then the outcome of one typically doesn't affect the other. Now, sometimes this assumption of independence is wrong, but it's good enough for us in terms of moving forward. What I mean by this is that if you have a finite number, and a lot of the problems that we're going to be dealing with are finite numbers. And what I mean by that, there are only 20 students. All right. If I select a male and then I go to select another male, the question comes, has the probability of selecting a male changed after I select one male? Well, if that same male cannot be selected again, then the answer is yes, the probability has changed. When talking about small numbers like 20 students, taking one of them out changes the probability pretty dramatically at times. But if there were 1,000, if there were a lot of students, if I was picking from all of BCLA, 500 students, and I selected a male, and then I go and I say, what's the probability that I select a second male? Well, the probability of the second male technically has changed, but it has changed very insignificantly. So, by small decimal percentages. So, in the case of statistics, you might be asked about doing calculations for independence. And typically, it's an assumption that we make given the idea of randomization. Now, some other vocabulary. So we have the multiplication rule of multiple independent events. And the rule says that when you're doing something twice, okay, thank you for letting me know. If you're doing something twice, and so if you do multiple selections, for example, you select two M&Ms, says that the probability of A and B happening, so you do A and B, this is equal to the probability of A times the probability of B. You multiply the probabilities. All right. And this can happen over and over and over. So if you're talking about, now this is multiple events. And let me be specific about that. This is talking about multiple events, multiple selections. All right. The other rule that we want to know is called the complement rule. The complement is the probability of not having an event, a specific outcome. We call this the not. So it's the probability of not getting A. We use the notation, the probability of, and there's two different ways to do it. I like to use the squiggly, so we say, you know, right here, not A. So that when in probability, utilizing that squiggly line means not. Sometimes you might also get, you might see the notation with a little C. All right, complement, C for complement. But I like to utilize the not A. The probability of not getting A is 1 minus the probability of getting A. So, for example, if you have a 30% chance of winning, what's the probability that you don't win? We have a 30% chance of winning. What's the probability that you don't win?
70%.
Yeah, and so how did you do that? You did 1 minus 0.3. You did 100% minus 30%. You know they have to add up to 100%. You know the probabilities have to add up to 1. So to find the probability of not getting that. Now, it's very simple when there's only 2, but if there's multiple events, if you have a red M&M, a green M&M, a blue M&M, you can, you know, what's the probability that you get a red? Well, you know how many reds there are. What's the probability of not getting a red, and so forth. So let's talk about single variable probability. We have a single variable, all right? There's two types of problems. There's single variable, and then there's two variables, okay? In this case, when I see talk about a single variable, it means that there's only one property that we're looking at, all right? And so, for example here, we have 50 M&Ms, that's the who, in a bag. 15 are red, 10 are green, and the rest are blue. What is my variable in this case? What's the variable? What's the
M&M's?
No, that's the who. What's the variable in this question?
The color.
The color, which is categorical. And most in all these problems, typically, we are talking about categorical, at least for today and then mostly this week. So we're talking about like a categorical type variable, and in this case, color would be the variable, and the options are red, green, and blue. Now notice I didn't tell you how many blue there were, but you can figure out how many blue there actually are. By how many blue are there? $25, thank you. There's 15 red, 10 green, that's 25, so the other 25 have to be blue. So my first question to you, and these are very traditional probability questions that you've been asked. What's the probability I select a red M&M? Now, one of the things that it's going to be a little bit tougher to do that versus what you did is using probability notation. So I put red, I could have just put R, you know, but red is not a big word and it's perfectly fine. So what is the problem that if I select one M&M, we're doing a single selection right here. If I select one M&M, what's the probability that it's red? So one of the things that you have to make sure you do is show your work. So because of that, we want to show the answer. What is that?
Yeah, 15 over 50.
15 over 50. This is work shown. Now the answer is as it was noted, 0.3. Okay, but in statistics, we must show work. So the fraction, you must show the fraction because the fraction shows work. And actually, that's good enough. You do not have to write the 0.3 if you don't want to. Most of our answers will be fractions. Okay. B, what's the probability of this? I'm not going to tell you what that means. Can someone tell me? Or actually, let me do it right here. What am I asking you for?
Probability of green.
No. Somebody else want to take an attempt? What am I asking for here? It's okay if you don't get it. You're not going to be asked for these questions using the notation. The notation is just something that we should be able to use. And when following my work, it's something that you need to be able to understand. So in the AP exam, you'll be given like a verbal question. What is the probability of not selecting a green M&M? So this question is saying not. There's a little squiggly line that's right in front of it, which means not. Okay, so you won't be asked that though. So one of the things, especially in today, we're learning notation. So it's okay to be wrong, especially today, with misunderstanding what the question is asking you or when it's working. So to speak up if you don't understand a notation. I'm trying to intertwine it to try to check it while we're learning it, but sometimes I can overlook something. The question would say, hey, what is the probability of not selecting a green? Now there's two ways of doing this. We can count how many non-green M&Ms there are. So we know, and sometimes the math is very simple. There's 10 green M&Ms. So the probability of not, how many non-green M&Ms are there?
Is it 40 out of 50?
Correct. Now you could have also have gone to that answer by saying the probability of not getting a green is 1 minus 10 over 50. You could have done it this way. All right, 1 minus 10 over 50, which gives me 40 over 50. All right, or you could have said that, oh, that's the same thing as 1 minus 0.2, so 0.8. So 0.8 would have been my answer, which is the same thing as 40 over 50. All right, so this is just another way of doing it. Now, if you, in these types of problems that we just did, this is a very obvious problem. And so just going right to the answer and showing the 40 over 50 is more than enough. Oh, and I forgot to put this other one. Addition property of probability. Forgot this one. I meant to put it up earlier, but I'll just put it right here. Oh. Before I get there, I have to do something else. I have to define something. Disjoint events. Two events are disjointed if they both cannot occur at the same instance. Does anybody know the other vocabulary word for disjoint events? Looking at this definition, they both cannot occur at the same instance, at the same time. You can't have both. There is something, you probably hear this a lot, like in history or even ELA class, especially. They don't use the word disjointed. This also has another word. Does anybody know or have a guess at what that word is? These two things are blank because they can't occur at the same time. And a lot of times, the truth of the matter is, you heard this word and you really didn't even know what they were saying. It happens all the time. It's two words, actually.
Is it independent?
No,
oh, then never mind.
It's two words. And the first word starts with an M. I'm throwing it out there. I mean, I'd be surprised if you can identify what that word is or what those words are. But maybe you know when it means that two things cannot happen at the same time. Independence means one thing does not affect the other. All right, one event does not affect another event. The other one, I think I gave enough time, and I'll give a last chance. Anybody? Starts with an M. The word is mutually exclusive. It means the same thing as disjoint events. And I'm sure you've heard someone use mutually exclusive. It's a probability, or it's an idea of that two events, two things, we call them events in probability, cannot happen in the same space at the same time. You cannot have these. So C, is color mutually exclusive? Oh, sorry. I had to add something out. Mathematically, we say that the probability of A and B equals 0. So the probability of getting A and B is 0. That's the mathematical. So C, is color mutually exclusive? Is color mutually exclusive? Explain. Talk about the colors of M&Ms. Are they mutually exclusive? Are they disjoint events?
No, because they all have one color.
It's the opposite. The answer actually is yes. They are mutually exclusive because M&Ms, each M&M can have only one color, i.e., the probability that you get a green and a red when making a single M&M is 0. You cannot select an M&M and get, oh, this M&M is green and red. So mutually exclusive, or saying disjoint, because each one can only be one. Everybody has only one response. This M&M is red. This M&M is blue. This M&M, is green. You cannot have M&Ms that fall under two choices. So mutually exclusive. in our course, and I want to put this out. In our course, we defined for the sake of probabilities and calculations, gender, for example, to be mutually exclusive. So, I do want to make sure that when I do talk about this in the future, just in case it does offend or goes against people's beliefs, it's not purposeful. It's just for the making of calculations in our course. When we talk about male or female, we will specifically say that those are mutually exclusive, so everybody will define themselves as being either male or female. Now, in society, in today's day and age as well, there's some people gender fluid and so forth like that. Um, we won't capture that within our data because in the purpose of our calculations and the type of problems that we're trying to do, it won't work for us in those instances. So I just want to just put that out there just to make sure that when we do and then say, like, please, I might ask you to identify yourself as male or female and so forth. One moment real quick. So probability, so the addition property of multiple disjoint events. And I know it seems hard to be able to track all these and the different ones. So, Anne's question, yes, correct. If and I know in we can talk about I've selected an M&M and it had like two colors and it was a weird merged one and stuff like that. We try at least in our course not to identify. We defined the colors to be mutually exclusive. Each M&M will be defined as being one color. But yes, and there's some M&Ms, for example, that have multiple colors. But in that case, we might actually define, for example, if there's an M&M that's like red and green, we might say there's red, green, and then there's red, green. So like half and half. We might define that as one of the colors themselves as a mixture. So right here, we're going to be talking about multiple events. All right. So when talking about multiple events, or oops, no. Sorry. That should have been single. We're talking about disjoint events. All right. Two things can happen. It's a single one. Sorry about that. Single. Please update that. The rule is that the property of getting A or B is equal to the probability of getting A plus the probability of selecting B. Now, you've done these types of problems, okay? So you've done A or B. And if I had just given you this question, you would have felt very comfortable. So for example D, what is the probability of selecting a red or blue M&M? So what's the probability of selecting a red or a blue M&M? And actually, we've already done this question. Basically, we've already done it. But I want to show you how the calculations can be different because there are going to be different way of worded question. And yes, it's 40 out of 50. So we're saying the probability of A plus the probability of B, which is 15 out of 50 plus 25 out of 50, which gave me 40 out of 50. Now, of course, you can just count all the red and blue M&Ms and you say there's 15 plus 25. However, I want to note that in this question, I gave you the probability. I gave you the numbers of outcomes. So often not given frequencies, but instead given probabilities. Now comes the idea of multiple events. Which we talked about that rule above. So you will be specifically stated. So in this problems, you are so for for the following problems, we select 3 M&Ms. So most of these questions on the AP exam and when I test you, the first questions will typically be you select 1. Okay? Then we change the problems and they say, okay, now we're going to select like 3 of them. So E, what is the probability of selecting 3 red M&Ms in a row? So we want to know what's the probability that we get a red, a red, and then a red. A red, red, and a red. Well, this is a multiple event. So when we think multiple events, most of the times we need to think about multiplication. All right? Multiple events, multiplication. We know the probability of selecting a red M&M is 15 out of 50. So the probability of selecting that first M&M, we have a first M&M, which is 15 over 50. Then we're going to select another red M&M, 15 over 50. And then we're going to select a third M&M, 15 over 50. This is the same thing as 15 over 50 to the third power. And when we plug that into our calculator, we would get 0.027. But please note that you also had to show your work. So you would have to have done that work from before. F. What is the probability all 3 are the same color? Now this gets interesting. So we went from just being specifically, what are the chances that all 3 are exactly red? Red, red, red. Now, if I said what's the probability that they're all the same color, what are the possible outcomes for 3 M&Ms such that I get all 3 the same color? What are the possibilities? What could I get for the same color? Well, first one I can get is red, red, red. Or what's another option that I can get? Yeah, in a row, yes.
Green, 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 and blue, blue, blue.
So to find this answer, I need to find the probability of red, 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 add it to the probability of getting green, 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 and add that to the probability of getting blue, blue, blue. There are 3 different outcomes that work. So even though we're talking about multiple events, the outcomes now, the sample space is rather large, all right? So I'm not asking you to do the sample space because you can have red, green, blue, red, 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 green, red, red, blue, red, blue, green. There's so many different outcomes. We'll talk about how those look. But in these problems right here, I'm asking you specifically 3 of the same color. You got to go, oh, okay, that can be red, 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 or green, 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 or blue, blue, blue. And now this problem asks you to do 3 probability questions. So my answer here would be, well, what's the chance that I get red, red, red? Well, that's 15 over 50 to the 3rd power. I get red, red, red. If you want to multiply them out, that also works. What's the probability of getting green, green, green?
Um, 10 over 30 to the power
50,
of 3.
50, 50.
Oh yeah, 50 to the power of 3.
And plus, what's the probability of blue, blue, blue?
Replace the 10 with 25.
Now you just plug this into your calculator, Desmos, graphing calculator app. Type that all in. Now, technically, this is the answer. So in our course, if you just left it like that, that is full credit, all right? You showed me your work, that is the answer. Of course, if it's a multiple choice problem on the statistics, AP statistics exam, we should get used to getting these answers. And so this answer would actually be 0.16. If the decimal number goes on and on and on, typically 2 decimal places is going to be good enough for us. I like to think of it as 2 non-zero decimal numbers is typically what we would like to use. So I was actually going to go into the other types of problems, but I feel that that might be something of an overload. So what I'm going to do is I'm going to update the homework and the homework problems. So because I need to do that, I don't want to go into anything a little bit extra on tops of these ones right now. Well, you know what? I do want to go in at least some more notation then. So since I'm not going to go into anything else, I do want to go into notation. And that is, notice that I had said the word or. We use the symbol U. So, in example, the probability of getting a red or a blue, we would write that as the probability of a red union B. So you might see these types of notations in solutions and work. The U means or. And so the rule is that the probability of red or blue is equal to the probability of red plus the probability of blue, given that red and blue are disjoint. So I just want to make sure you see that. And we use an upside down U that also refers to the word intersection, i.e. the probability of selecting a red and a green, or a green, we'll say green this kind, is equal to the probability of red and green. Okay. Given that these are multiple events, the probability of red and green is equal to the probability of red times the probability of green. So those are the notations where we'll we'll link them into the problems as we go on. I did want to show you those. I'm going to update the homework assignment, and since we're learning a lot of vocabulary, and I know it's even made more difficult by the fact that we are remotely, I'm going to end the lesson there. Give me about 5 minutes to update the homework problems before you start attacking them. Beyond that, I will see you tomorrow. Take care, everybody.